Welcome back, Math 253, Calculus 3, Cañada College. My name is Ray Lapuz. We are now diving into section 2.4, the cross product. As our second type of product, actually third if we count scalar multiplication, we've finished the dot product. Now we're going to dive into the cross product. The cross product is going to be our first product where we take the product of two vectors and we're actually going to get another vector out of it. So in terms of the definition is kind of complicated. It's not something that we would try to remember, but it looks something like this. Well, instead of spouting that off, we're going to take a look at the geometry of this, and then a little bit later on, we're going to try to find an easier way to calculate the cross product. But in general, if you have a cross product, again with the right-hand rule, what we could do is we're crossing u with v, so that's u cross v. And if we cross u cross v, you're going to take your right hand, wrap your fingers around the u vector first, and then wrap your finger around to the v vector. And then your cross product, your resulting cross product, will be a vector that is going to be perpendicular to both u and v and going in the direction of your thumb. Now, if you have two vectors, u and v, there's two possible ways of finding a vector that's perpendicular to them. You can have a perpendicular vector that goes up, or you can have a perpendicular that goes down. But if you have a u vector and a v vector, and you take your right hand and you wrap your fingers around first the u vector and then the v vector, then your thumb is going to be pointing in the direction of the cross product. Again, we're using the right hand rule. Some properties of the cross product. First of all, the I, J, K are three-dimensional standard basis vectors. And if you cross I and J, you're going to get K. That's like the X and Y. And using your right-hand rule with the X and Y axes, you're going to get the positive Z axis. And then if you look at the other combinations of cross products here, JK is going to give you I, KI is going to give you J. Now, if you have J cross I, kind of backwards, then you're going to get negative K. And again, the right-hand rule is going to apply. Speaking of the cross products and switching the orders of the cross product is what we call anti-commutative. It's not a commutative vector, because if you switch the order that you're taking the cross product, you're going to get a different answer. But the different answer isn't so different. It's just the negative of what you would have got. And that's why it's called anti-commutative. We also have a distributive law, just like we did with the dot product. We have the multiplication by constant law. This is kind of similar to the associative property of the dot product. We have the cross product of the zero vector. If you cross anything with a zero vector, you're going to get zero. A cross product of a vector with itself is going to give you zero. So that's another interesting property. And then what we have is a triple scalar product. And the triple scalar product says that if you're going to take the dot product of u with the cross product of v and w, then it's like taking the cross product of u and v dotted with w. Now you can switch some of these around, but a few other switches might make this negative because of the anti-commutativity. But in any case, the scalar triple product is an important aspect of some computations that we might have to do. Now, to try to find the cross product without having to remember that scary looking definition, we have a more systematic way of establishing the cross product. And that's going to be based on determinants of matrices. And the idea is, I know this is linear algebra, but the idea is that we have to know the determinant of a 2x2 matrix first, and that's going to be defined by the matrix A1, A2, B1, B2 in the second row. The determinant of that is going to be the product of A1, B2, which is kind of like running along the diagonals, minus the product of B1, A2, which is what we call the wings for a 2x2 matrix. So it's the diagonals, the product of the diagonals minus the product of the wings. Now for a three-dimensional, or for a 3x3 matrix, One way to find the determinant is to expand. They call this expanding along the top row, where we have A and then the determinant of the 2x2 submatrix, that's B2, B3, C2, C3. And then the next term is A2, but this is important. The A2 is going to be negative. So it's negative A2, and then imagine crossing out the row and column where A2 is, and then the remaining matrix, the remaining 2x2 matrix would be B1, B3, C1, C3. And then you take the determinant of that. And then finally, finishing up the first row, we have A3 positive, and then cross out the row and column in which A3 is in, then your remaining matrix would be B1, B2, C1, C2. So generically, for any two vectors, if we lay those two vectors as the second and third rows of a 3x3 matrix and let the top row be the ijk vectors, then we can imagine the cross product to be the determinant of this 3x3 matrix. Now, if you do the computation here and compare it with the definition that we saw early on, you'll see that you're going to get the exact same answer. But this time, you're doing this so that you don't have to memorize that complicated looking formula. Just remember that you're taking the determinant of a 3x3 matrix. Well, if you might think the determinant might be too cumbersome to try to memorize, then think about if you're ever going to take linear algebra, you have to know what a determinant, so you might as well just stick with that. Okay, now that we have a way to compute the cross product, and now that we have a way to or now that we also have some ideas of some of the properties of the cross product and some of the geometry, we can continue to apply the idea of cross products with things. So one important idea that's using the cross product is that it happens to be the area of the parallelogram. So if you have two, well, not the cross product, but the magnitude of the cross product. So the idea is that if you have two vectors, u and v, it turns out that the magnitude of the cross product of u and v is actually equal to the area of the parallelogram. So that's an interesting fact about the cross product. Another interesting fact is that if you imagine a three-dimensional parallelogram, well, it's going to be a solid, so it'll have parallel sides instead of parallel faces instead of just parallel sides. We have what's called a parallelepiped. And it turns out that the volume of the parallelepiped is exactly the triple product. Now, the triple product could give you a negative number if you remember if the dot product of two angles that are obtuse. So if that happens, then just take the absolute value and then you should be all good in finding the volume of the parallelepiped. So in general, volume of the parallelepiped is the magnitude of the triple product, or the absolute value of the triple product. All right, one more important physics application to the cross product is the torque. And the torque kind of measures the force that you're putting on something as you're spinning it around. So imagine you have a wrench and you're trying to turn the wrench to loosen up a screw. The longer your wrench is and the farther out along the wrench you hold, the more force you're going to exert, the more torque you're going to have. If you have the wrench and you hold it near where the screw is, that's not going to give you that much force. And so the longer your R is, in this case the length of the wrench, the easier it is going to be for you to turn it. So that's the physical representation, or one of the physical representations of the cross product, is a torque. Okay, so that's our quick overview of the cross product, and good luck with all the problems in this section.